It is possible to use the clotting app to analyze results from halo assays. Here I will explain how this can be done. The halo method was developed and published by Bonnard et al. In 2017, and is simply summarized in this figure. A small volume of thrombin solution is mixed with whole blood to form a circular clot around the bottom of a well of a microtitre plate. After the clot has stabilized, a solution containing a thrombolytic agent is added to the well. Initially, the light can pass freely through the hole in the middle of the clot through the clear solution. As the clot breaks down, the surrounding solution becomes red and the absorbance increases. The assay provides an interesting approach to measure fibrinolysis using whole blood, and can be used to investigate different thrombolytics or fibrinolysis inhibitors, for example. We have used the method to investigate the antifibrinolytic, tranexamic acid, together with TPA as the thrombolytic, as shown here. In this plate we have increasing concentrations of TPA across the columns, and decreasing concentrations of tranexamic acid down the rows. Therefore, we expect slower lysis in the top left and faster lysis in the bottom right of the plate. We have also used a variation of the assay using clots made from plasma, with added fluorescently labeled fibrinogen. In this way, we could investigate clots without any cellular components in the same setup as the whole blood halo assay method. In both these cases, data were analyzed using the clotting or halo app, which can conveniently measure the time to a fixed percentage of lysis. The app also calculates the time at maximum rate of increase, as shown on the plots as the magenta line. This is often very close to the time for 50% change, clotting or lysis, but less reliable in my experience. When setting up a halo assay, it is recommended that wells are included in the plates that have blood clots with no thrombolytic, and also blood without added thrombin, so that the baseline and final absorbance values are established. These result in flat responses which can cause some problems when loading data, but I will demonstrate how to deal with this. When loading data from a halo assay, you might initially run into this error message, which arises because of the wells containing unclotted blood and high values. The simplest way to deal with this is to increase the interpolation threshold value. I know in this example that increasing the value to 1 will work, but you may need to go as high as the highest absorbance value in your data. When the threshold is 1, the plots appear. In this case, there are 2 columns of duplicate conditions where TPA is the thrombolytic and tranexamic acid diluted down the rows. The top row has no TPA, but we usually do see a slow increase in absorbance. The bottom row is the unclotted blood, which gives the endpoint reading you would expect for complete clot lysis. Now it is necessary to adjust some other settings, including the baseline and maximum options. To enter the best option, it is necessary to take a look at the raw data. We can see here that the first readings across the wells are quite high but also rather variable. So it will be sensible to change the baseline option to the first point or minimum. In practice, it looks like it won't matter which one of these options is chosen, as the first point seems to be the minimum value. It also makes sense in halo assays to choose a global maximum, which is the value from the wells that have no thrombin added. In this example, row H was not clotted, and we can see a value around 4. However, this is not a real value, rather the plate reader has just maxed out. So if we go back to the Plots tab, we can make these changes. Now we can see that we are getting less lysis at the top of the plate, but in fact not achieving 50% lysis in many of the wells. In this case, we might be able to get a little bit more usable data if we reduce the percentage of lysis. For example, let's try 40%. In a repeat study, you might want to adjust the concentrations of TPA and tranexamic acid to optimize the range of lysis times. To get a quick look at what these results show, we can go over to the Explore tab and look at the heat map of the plate. As expected, we are seeing faster lysis as we go down the rows, as the tranexamic acid concentration decreases. The scatter plot indicates that there is a good dose-response relationship with time to 40% lysis. By contrast, in this case we can see that the time to maximum rate change does not correlate well with tranexamic acid concentration. As I mentioned earlier, we have also developed a method that uses the halo setup but with plasma, and added fluorescently labeled fibrinogen. You should note that when using fluorescence, your global maximum will be very different. You can see in this case I have entered 60,000. I have also managed to get more useful data from this plate by selecting 20% lysis. I hope this brief demonstration is helpful if you want to try out the halo assay. It's an interesting approach to measuring fibrinolysis using clots made of whole blood. The Clotting or Halo app provides a simple and reproducible way to analyze data from Halo assays. If you have any questions about the app, please get in touch using the email address in the Help tab. Good luck!